Welcome to our journey into the world of software design concepts. Here, we'll explore the foundational principles that guide engineers in modeling systems before they dive into coding. Software design concepts are foundational principles, for example, abstraction and modularity, that guide how engineers model systems before coding. They bridge the gap between problem requirements and technical implementation. As M.A. Jackson once said, there's a distinction between functional code, which is about getting it to work, and well-designed code, which is about getting it right. This highlights design as a deliberate, thoughtful process. Think of design as creating a scalable, maintainable model of the system, much like an architect's blueprint for a building. Abstraction hides complexity by exposing only essential features. For example, a vehicle class hides fuel mechanics but provides the ability to drive. It operates at various levels, from high-level system architecture to low-level code implementation. This approach reduces cognitive load, allowing engineers to focus on interactions rather than internal details. It also enhances reusability, like abstract classes in object-oriented programming. Take WhatsApp's chat system design, for instance. It abstracts the intricacies of message delivery so users don't need to know about sockets or protocols. Modularity splits software into independent modules such as authentication and payment processing. It's like assembling Lego blocks where each piece has a specific role. According to Buch's principle, high cohesion means modules should have a single, focused responsibility, while low coupling minimizes dependencies between modules to avoid ripple effects. Modularity enables parallel development, allowing teams to work on separate modules. It also simplifies debugging by isolating faults to specific modules. Encapsulation is a fundamental concept in object-oriented programming. Classes encapsulate attributes, for example, balance, and methods, for example, withdraw, into a single unit. Private variables, such as balance, enforce controlled access via methods. This prevents unintended data manipulation, for example, negative balances in a bank account. Think of WhatsApp hiding encryption details while exposing send message functionality. Encapsulation stands as a core OOP concept alongside inheritance and polymorphism. Functional independence is crucial for building robust systems. Each module should perform one subfunction, for example, calculate tax in an e-commerce app. Simple interfaces reduce integration complexity. Cohesion is the measure of a module's internal focus. High cohesion is good. Coupling, on the other hand, is inter-module dependency. Low coupling is good. This approach reduces error propagation, meaning changes in one module rarely break others. Refinement involves breaking down high-level functions, for example, process order, into granular steps, such as validate payment and update inventory. This method is complementary to abstraction. While abstraction hides details, refinement adds them incrementally. It starts with broad design models and ends with executable code. This hierarchical approach ensures that each level of detail is addressed methodically. Refactoring restructures code, for example, renaming variables, splitting methods without altering external behavior. Adding features, fixing bugs, or improving readability can trigger refactoring. The benefits include reducing technical debt and ensuring the code base remains adaptable. Architecture defines how modules interact. For example, in a layered architecture, the UI communicates with business logic, which in turn interacts with the database. Patterns like layered architecture isolate concerns, for example, separating presentation from data layers. Microservices, on the other hand, decouple services for scalability. The goal is to provide a framework for detailed design and scalability. Patterns offer reusable solutions to common problems. For example, the singleton pattern ensures single-instance access, such as a database connection pool. This standardizes best practices and speeds up development. A well-formed design emphasizes clarity and completeness. Your code should be self-documenting and fully solve the problem at hand. High cohesion and low coupling result in maintainable design, with focused modules and minimal dependencies. Independent modules also simplify unit testing. Let's go over some key points. Refinement involves top-down stepwise elaboration, which is the correct approach. Case tools, or computer-aided software engineering, automate design tasks, making the process more efficient. Design class traits should include high cohesion, low coupling, and clarity, so the correct answer is all of the above. To sum up, the recurring themes in this document are modularity, abstraction, and encapsulation, which serve as the pillars of robust design. Design patterns like singleton and architectures like layered provide actionable templates to follow,